We will now discuss the shear force and bending moment diagram using graphical method. In order to be able to draw the shear force and bending moment diagrams graphically, we have to understand the relation among load, shear, and moment. Once we are able to find out the relation between load, shear, and moment, we would be able to construct shear force and bending moment diagram without writing shear and moment equations. We will see that the relation among load, shear, and moment follows equilibrium and the same logic as shear and moment. Now let us derive the relation. Let us beam is subject to some varying load which has a magnitude W of x. Notably, the load is varying along the length. We take a small portion of this beam and try to apply equilibrium on this free body. Since this portion has been taken out of the main beam, so we will have to apply the effects of the omitted parts. So the left omitted part will have its own internal shear and moment being applied onto the free body, and the right omitted part will have its own internal shear and moment applied onto the free body. This whole free body should be in equilibrium if our structure as a whole is in static equilibrium. On this portion, we have load Wx applied, and the total load will be Wx times delta x. The direction of shear and moment at the right hand side of the free body is in accordance with our sign convention. Our sign convention, as we defined earlier, is shown in this figure. Thus, positive load is facing up. Shear is considered as positive down for the left section of the beam, and moment is considered positive if it is in counterclockwise direction for the left portion of the beam. As we discussed, we normally consider the left portion and of the beam and omit the other portion. So we normally go from left to right within the span of the beam. So shear and moments at this section are at the right side of the free body are taken positive in accordance with our sign convention. The direction of the shear and moment on the left hand side of the free body are in accordance with the equilibrium conditions. Thus, summation of Fy must be equal to 0. So we will have V applied up, which is positive because our load in upward direction is taken as positive, plus Wx times delta x, which will give us the magnitude of the varying load, minus V plus delta V. The last term is negative because shear is facing down, or the load is facing down. V will get cancelled and we will get delta V is equal to Wx times delta x. Now taking moment at about point O, we get minus V times delta x. So V times delta x cause clockwise rotation, minus M, which is again clockwise, so negative, minus Wx times delta x, which is the load. Wx times delta x is the load magnitude times delta x. The K factor is applied to adjust the magnitude of this varying load. Since this is a non-uniformly varying load, therefore a K factor has been applied to adjust the magnitude. K is not very relevant to us. If we cancel out our M, we will get delta M equal to V delta x plus Wx times K delta x squared. And delta x being the small quantity, if squared, will become even smaller, and that will make this term equal to 0. In other words, if we reduce the length delta x further, we should be able to make this term equal to 0. If the length is reduced to an infinitesimal level, then we can convert our delta v and delta x as dv, and similarly delta m and delta x as dm by dx. Thus, we get two conditions. One is the slope of the shear diagram at each point is equal to the magnitude of the distributed load at that point. So dv by dx is equal to w of x. The second equation is the slope of the moment diagram at each point is equal to shear at each point. So dm by dx is equal to v. These two equations help us drawing shear force and bending moment diagrams quickly. We can also integrate these two equations. So first of all, the first equation, dv by dx is equal to w of x. We can integrate that and get an equation. So the change in shear between point 2 and point 1 is equal to the area of the load between point 2 and point 1. Similarly, the change in moment between point 2 and point 1 is equal to area of the shear force diagram between point 2 and point 1. We can also illustrate this principle by considering the simply supported beam, which is subject to some variable loading. So the change of shear between x1 and x2 should be equal to the area of the load diagram between x1 and x2. So the area under the curve between x1 and x2 should give us the change in shear between these 2 points. Similarly, the change in moment between x1 and x2 should give us the area of shear diagram between x1 and x2. Please note that based on the sign convention for the derivation of the shear slope and moment slope equations, the positive slope is facing up as shown in this figure and the negative slope is facing down. Now let us apply these concepts on a simple problem of a simply supported beam subjected to a concentrated load at point B, which is the midspan. So after applying equilibrium, we'll find out that at the reaction at A is P by 2 and similarly the reaction at C is P by 2. So we have at A a positive shear force. We can see that there is no load in the segment AB. Thus, the shear force will be 0. Because of the discontinuity produced by the load P, we will have a sudden drop down. Again, between section B and C, there is no load. So the shear force diagram will have a 0 slope. And finally, at point C, it will come back to 0. As we discussed that the difference of moment is equal to the area of shear force diagram between the 2 points. So if we consider point A and B, then the moment at point B will be equal to the area of the shear force diagram between section A and section B. This positive area will give us the magnitude of moment at midspan, which will come out to be PL by 4. The shear is positive, thus our slope will be positive. And as we said, the positive slope is facing up like this. So the first part of the bending moment diagram will be having a positive slope. After that, segment BC has got negative shear, which means to say it will have a negative slope, and there will be slope which is negative as per this figure. We can apply the same concept for a problem for the beam, simply supported beam subjected to UDL, so a positive shear. And since the load is 0 degree, so shear variation will be first degree and moment variation will be second degree. Hence, a parabolic curve in case of moment and a straight line having some slope in case of shear. Now again, we can find out the area of this positive portion of the shear force diagram. The maximum moment, we can get the area of this right angle triangle. So half breadth into height will give us WS square by 8. So again, the maximum moment is equal to the area of shear force diagram. Shear at the left support is finite, hence we have the slope of the moment diagram, which is a finite value, and that comes to zero as we move towards the middle point or to the mid span. This is in accordance with the value of shear becoming zero. So as we said, that rate of change of m with respect to x is equal to the shear. So if shear is zero, the slope of the moment diagram must be equal to zero. And that we can see over here that the slope becomes zero. After that, the slope becomes negative. So as per our convention, the negative slope is in this direction, and we can clearly see that a negative slope pairing and its value increasing as we move toward the right support. And this is because that our shear value is increasing in the negative direction.